We took a video here about 7 hours ago. Now it's almost 7:43 p.m. I took the video about noon time. At noon time, you did not see this coloration in the horizon. You have the orange, the yellow, you start having colors beside the blue and the white. And we commented on Stefan-Boltzmann law. Why do you see at noon time you see only the blue and the white? The spectrum is there. You have all the colors of the spectrum. But the spectrum depends on, the spectrum means the wavelength of light. The peak of the spectrum is around 450 nanometer, which is about almost half a micron. That is around the yellow line. So why do you see white? It's because you have all the lines of the spectrum are intense. Stefan-Boltzmann law simply states that the spectrum, the intensity, depends on the absolute temperature of the source to the power 4, the fourth power of the source, multiplies by Stefan-Boltzmann constant. Remember, that law was formulated before the discovery of the nucleus and before the identification of the electron. As a matter of fact, Max Planck himself could not find a definition for the absolute temperature. How do you formulate the temperature of the atoms in terms of the parameters of the atoms, which are the atomic number, the atomic weight, the electron charge, the proton charge, the number of protons? So Stefan-Boltzmann law was empirical. The reason that you have the T to the power 4 is because you have two spheres. The sphere of radiation that is centered on the source and the sphere of reception that is centered around your own eyes or as the target where the radiation fell from the source. So when you divide the intensity of the source by two spheres multiplied by each other, so you have r squared times r squared in the denominator. So you have T to the power 4. It was an empirical law. Simply means a source that radiates the radiation that you receive as the detector is only a minute fraction. Depend on the temperature of the source to the power 4. Remember, that means the source is so strong. Why? Because the source radiates on a sphere in all directions, and you receive a fraction of your own sphere. That is why you get Stefan-Boltzmann law. Well, how do you apply it to the situation we are in now? The sun, I have to say, the temperature of the sun is about 5,500 degrees. Stefan-Boltzmann law have to be also combined with the square law of radiation. So you are sitting here, the further the sun is away from you, the lesser the temperature that you are going to feel here. So when the sun is perpendicular in the skies afternoon, you see the entire spectrum of the sun. The entire spectrum is very intense. So you get the entire visible colors, from the blue, the green, the yellow, the orange, or the red. That is the visible spectrum. When you add them together intensely, you have the white coloration at noon time. Now the sun is in the close to sunset. So the temperature that you are going to feel is going to be much less. As a matter of fact, you are just having a portion of the entire spectrum reduced because of the distance increased between you and the sun. So the same spectrum that was there about 6 hours ago only changed in the intensity of each wavelength of that spectrum. So now you start seeing the coloration around the sun. You can see a red now, you can see the yellow, you might not see the orange, but what you see above you in the sky, the white means intense mix of all the spectrum. The gray means the part of the cloud is not subjected to radiation, so it looks dark compared to the surrounding. Above me here you can tell you are going to start seeing reflection of the yellow, of the green. You don't see green now, but you see the yellow and the blue. Within almost few minutes from now, an hour, we are going to see a dramatic change. The entire spectrum will shift towards the red. The shift is the intensity, remember, because the intensity of the other colors, other lines, decreases. You are going to have shift towards the red. And when the sun is in the horizon, you're going to have the infrared, which is invisible.